revised energy balance. Okay, so without thinking about it, I left us a spot, so that's nice. So we'll just put a value here, just 1 for the time being. Right? So this is an equimolar feed of inert and A. And now we need to modify which equation that we see here. Epsilon needs to be modified. So what was epsilon? It's now equal to 1 divided by 1 plus theta. So that changed it to 0.5, which makes sense, equimolar feed. Anything else change over here? CAO, right. So now this is not this one, it's actually this one, which is the one that was kind of always should have been. And before it was just this stuff, and now it's this stuff times the same thing, 1 divided by 1 plus theta pi. Okay, so the initial concentration changed as we might expect. Is there anything else over here that changes? Gas constant's constant, dV is a parameter for our spreadsheet. It doesn't really, matter in that sense. Initial temperature doesn't change. What about the pressure? Do you have to worry about like a mixing effect of the pressures for these two streams?
Are the temperatures the same?
The temperatures are the same, so are the pressures. So that was also in the problem statement. So you don't have to worry about, will the initial pressure change? No.
What do we do if they're different? Or we'll just do it?
You'd have to do some ideal gas math and figure out if I mix two streams at different pressures, what's going to be the final pressure. That's mass and energy balance. Initial concentration, we updated that. Epsilon, we updated. The initial flow rate of A doesn't change. Nothing else up here changes. Okay, what about our formulas on the left? Volume's not a formula. Does our design equation change?
The way you made it, I don't think it does.
No, right? Because the concentration is the only thing that changed and epsilon changed. We've already accounted for both of those changes. The form of the design equation didn't get affected by whether or not there was an inert. What about this energy balance equation? Yes. Okay. So I wrote it a little bit differently than we wrote down on the board, but it's not a big deal. So where I have here I9, that is the heat capacity of A. And now instead of just having that, I have to include theta I times the heat capacity of I. And those are both in column I. And then down here, I have to include the same thing. I'll make it bigger in a second. So all I did is there was a couple places where I had I9, which on my spreadsheet is heat capacity of A. Now I've had to replace that with the sum of heat capacity of A plus theta I times heat capacity of I. Still can't see it? I'll zoom in. Go a little bit further. Everybody see that? Everybody good? No? Okay. Good. Okay, I heard less objection there. So let's do a gut check. Hey, look, if I set theta I equal to 0, we get the same conversion, the same temperature. So we haven't broken anything yet.
I still don't have that last one.
Okay. Yeah, it's just wherever there was a heat capacity of A term, we replace that with heat capacity of A plus theta I times the heat capacity of I. And the way I input the formula, there were two heat capacity of A terms. You could have input it with only one of those terms, but I'm done. All right, so if theta I is 0, nothing has changed. So this is just a nice thing to do to make sure you didn't break something when you modified all these formulas, right? If you put a minus sign where there shouldn't be, or you forget a plus sign or something, you can break these things pretty easily. This just tells me I didn't break anything. And now we'll put in a value of 0.1. One thing I want to do before we do that is I'm going to fix these scales, because I want to show what happens so all I'm doing is I know that the drop in temperature is going to be less severe. So if I make this 900, I don't have to worry about the temperature profile going beneath 900. Because we already heard that increasing the amount of inert will make the temperature drop less severe. For conversion, I just chose 0 to 1 because that's the limit on conversion. All right, so now let's change this to 0.1. And I'm going to hit Control Z and Control. Oh, I went too far. That's too subtle. There we go. All right, so I go 0 to 10, and you see that temperature profile shot way up. The conversion, though, went down. So even though we're mitigating the temperature loss, we're still diluting our concentration of our reagent, which in this case has caused the conversion to drop. Everybody see that? So the conversion at 500 was 0.36. We go to 10, it's dropped to 0.24. But the exit temperature was 930, and now it's up at 986.
Theta I only vary between 0 and 1.
Why? Theta I is the ratio of the inerts to the ratio of your feed. It can be any positive value.
Yeah.
Okay, so the problem goes on to ask if there's a maximum here. So if we were to look at, if we want to maximize the conversion in our 500 liter reactor, how much theta I do we want? Now we've seen two extremes. No theta I, we get 36% conversion. If I go to a huge amount of inert, I get 11% conversion. So obviously, over the whole scale, theta I will decrease my conversion. But is there ever a point where it goes to a maximum? So if I plot, I know this is hard to see because it's dark, but if I plot the conversion at 500 liters versus theta I, we have two data points. One is at 0, we get 0.36 or 38, I can't remember. At theta I of 100, we had 0.11. The question is, does it go like this, where there's a maximum, or does it simply decrease the whole time? So how can we find that out? What's that? Goal-seek? We could. Yeah, no, absolutely we could. We could ask. I like solver better than goal-seek. I don't know if that's in here or not. I don't think so. I know I can add it. We'll do that real quick. Hey, there it is. So yeah, I could try using solver. So what do I want to set the objective? I know this is hard to read, but what's the objective cell is conversion at 500 liters. I want to maximize that, is what that reads. I want to do so by changing theta I. And then I just hit solve. And it sets theta I to 0. So in other words, it's telling us there is no maximum within this profile, right, for these settings. Now that's not to say for every endothermic reaction this will be true, but it seems to be true for this one. There's another thing that we can do though, because I do think that the problem specifically asks you to plot this. So let's make a plot. We're in Excel, right? Let's make a plot. So the easy way to do that in Excel is not set up 15 of these sheets that are all identical except theta I is different. What I'm going to do instead, I did not put these next to each other by accident. What I'm going to do here is I'm at theta I equal to 0. I'm going to copy these cells. I'm going to make a new sheet. And now I'm going to paste. But when I paste, I'm going to paste just the values. Any questions? I don't think it would make you a plot. Now I change theta I, and I do it again. I'm just pasting the values, not the formulas, because they won't work. So I'm just going to put in some data points here, not a lot. You might notice I often change things in a geometric series. Don't pay attention to me, I'm a crazy man. It's habit.
For the next test, will we need the computers for it?
No. But a lot of the homeworks will require this kind of thing. It's the limitation of this type of course. There's a lot in